All right. So everybody, welcome to this live demo. Very excited to give this because it's a first time that we're going to see PAR being used to write a real program, not just a toy program. A real program, a small one, but still very real. So what is PAR? Well, I started working on this language, I think about like 8 months ago. So here's the GitHub repo. And I started working on it because I was learning about linear logic and session types and all these new ideas about structured concurrency. And there was so much of that in the papers in the academia, but I saw very little of it translated into practice. It became quite clear why that was. It was because the papers saw everything beautiful, theoretical, and like obvious potential in the structures that he created, the types, all of that. All the syntaxes they used for actually writing that code were just horrendous. And that's not because like the researchers are stupid. It's actually really hard to come up with good syntax for these semantics. But I thought I'd give it a shot because I really love designing libraries and designing programming languages, and I had some success previously. So I gave it a shot, and I think I succeeded. So PAR, I would say, is on a good trajectory to put all of these ideas into practice. Of course, for it to put it into practice, it actually needs to have all the functionality that's needed to write practical programs. That's the crux of what's actually new since recently. We are only starting there, but what's new in PAR and why only now is the first time that we're giving a demo that's about writing a real program in PAR is because only recently we added strings and numbers. Until now, actually, PAR was a very abstract language, sort of like lambda calculus, that you can program anything in it, but it doesn't have any I/O and it doesn't have any primitives. You can only program like abstract structures and algorithms on them. So now we have strings and numbers in PAR, and we also have some I/O. The foundation that PAR has for I/O is actually very powerful, but so far we only have implemented only some I/O, which is here. If we go into built-in definitions, here it's like listed. So we have like some storage capability, actually only for traversing directories and reading files, which we're going to be using now. Also writing to console, printing, prompting, fairly useful. That's about it. And then like different functions for working with the primitives and some other helper stuff. It's still like very minimal, but we'll see it's actually quite capable. Okay, let's get into it. I want to say I will not be explaining the whole language here. Read the documentation for that. I will be explaining some important things that we come across, of course, but I will mostly be showing what it's like to be programming in PAR. The program that we're gonna make is like small, but it shows a lot actually. So what is the program? Well, it's going to be like a mini grep. Just grep is this program that you can like search your files with. So this program that we're gonna make is going to be able to traverse a directory, search every file, and print all the lines that contain some string. I can now run the playground like this. Oh, actually, let me make a little folder here. So live demo, playground. Okay. So this starts playground, which is like the development ID right now. So let's get onto it. So we're going to be reading files. We're going to be scanning their lines and searching for those that contain a string. So the first thing that we need to do is to be able to separate lines. If we go into these built-in definitions, there is one thing here for analyzing strings, and that's this string reader. And it's like a very scary looking type, but we'll see that it's actually not that scary at all. And this string reader is very useful because there is this function, string reader as well, which can take a string and make a string reader out of it. But also, when we have a file, we can read UTF-8 and we get a string reader. So both files and local strings can be analyzed via this string reader. So let's study it a little bit. Let's ignore this recursive iterative part for now. There is this choice. Now, if you know par well, you know what a choice is. But maybe if you don't, then a choice is like a method dispatcher. It's an object where you can call any of these methods here, and you will get whatever is after this arrow. Or you can also supply parameters for some of these methods. But par being a linear language, this choice is a linear type, meaning you can only call one method and then it's gone. Then you get whatever is here. However, it would be useless, of course, to be calling just one method on a string reader like this. We want to like read multiple times. So that's what this recursive and iterative part is here about. Par has anonymous self-referential types. So you cannot actually reference types amongst each other in a cyclic way. Like string reader cannot mention string reader in itself. So we have to use these anonymous self-referential type. That's very good for totality, which par is aiming for, and in this program we'll have it. So this self here is referring back to this recursive, and this self attempt is referring back to this iterative attempt. This is a label. So that means that when we go all the way here, we have this again. So we can then call another method. So what can we do with the reader? Well, we can close it. We can get the entire remainder. Now this result is just like a Rust's result, like error or OK payload. But it has type arguments in the opposite order. The error is first. Okay, we can read one character, which either gives us a character and ability to call again, or it says that we reach the end, which is either okay or an error. This is the unit type, like an empty tuple. But there can be an error. In that case, we get an end and it is reported. And either is a sum type, like Rust enum. Then there are, okay, these two wonderful methods, match and match end. Match end is just like match, but matches to the end of the string. So here I did something unusual in design of this string reader, because I designed the universal match function that's useful for reading almost anything. So what is it about? It takes two patterns here, and patterns are described here. What is this? This is algebraic data type for regular expressions. It is an either, so a sum type, and it can be so empty or a string constant or one character of a character class, or we can repeat or concatenate, intersect, union. So we can build up regexes, and then we supply two of them here. And then we can get three kinds of results. One is that either an error happened or like we reached the end of the string. Fail means that the pattern did not match anything. Or we get a successful match. In that case, we get two strings back and then we go back to reading. So how does this work? So we supply these two patterns and we are matching on a concatenation of them. Let me show what I mean. This is not going to be like a runnable code right now, but say for example that we have a string like this. So some A's, some B's, some C's, and we have like a reader and we match on it. And as a pattern, we repeat, so we repeat one character class. So where's character class? That's here. We can supply a specific character as well. So repeat one char A. So this is a pattern that's like any sequence of A's. And say the second one we do repeat, but repeat one, which means at least one, char B. You might guess that this is going to match like all of this. That's correct. But why is that? The way this works is we take these two patterns, we concatenate them, and we are finding something that matches the concatenation of these two patterns. But there may be multiple options, right? Well, I mean, this is also an option. So which option do we choose? Well, I was thinking very hard and I found a strategy that works for all purposes that I could think of. It works really well. The way it works is among all the matches that match the concatenation of these two, we find the one that has this part smallest. That may still be many matches. And then among those, this part will be maximized. So since this is repeat 1, we need at least one B. So this will not match, not match, blah, 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 blah. Here it starts matching. The left part is this, but this matches 2 and the right part is longer. So we are taking that and so on. Since we are maximizing the right part, we are going to get all of these B's. Now, how does that work if we want to match a single line? So we remember that this character class also has any. So if we do any here, then we would do exactly a new line. For example, then we can have a string like blah, 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 a new line, blah, blah, blah. What matches these two patterns? This, but also this, right? However, we are always taking the shortest left part, and among those, the longest right part. We'll be taking this, and so that's the first line. Okay, so let's try to make like something that turns a string into its lines. So we're going to make a function, it's like lines. And we are going to take a string reader directly. Okay, it has a generic error. We're going to, for now, use a no error, which is exactly the kind of reader we get from reading a string. So this is an empty sum, no error possible. And we are going to return a list of strings. Okay, so let's see how we would implement that. We have a reader. Now, also an important part about this reader is that it's recursive here. Recursive is finite, meaning we can go through these selves only a finitely many times. Well, that means we can loop on it because we are guaranteed to reach the end. We won't get stuck in an infinite loop if we just follow these selves blindly. And you might know that par has inline recursion. We don't do recursion by calling the function manually, but we have inline recursion. So on a recursive type, we start the inline recursion by a begin. Now we want to match. That gives us this sum. So we're going to pattern match on it with case. If it is end, we can just drop this and we have an empty list. If we fail to match, that means there is no new line anymore. That doesn't mean that it's empty. I mean, otherwise we would get this end. So we still need to get the remainder and put it in the list. That's what this remainder here is for. Okay, that gives us a result, even though the error is impossible at the moment. Error, impossible. Well, that's an empty sum, so we can just do the empty case like that and that's sorted. Or we get some content here and then we put it into item and then we finish the list. This is how linked lists are done. They are defined also here. So recursive and or an item. We can also get a match. In that case, this first part is a line. And in this case, we produce the line. Okay, I guess let's also name this line. Oh, and there is also a reader here. Now we're going to loop back. So this reader is ready to be looped back. So we loop. There is one important thing here that I forgot to mention. Match only matches non-empty strings. It will never give you an empty match. At least one of these parts is a non-empty string. That is super important because if it could give you an empty match, then this remainder reader could be in the same place as when we started. So looping back, we could get an infinite loop. But that's why it only gives you a non-empty match, and then this remainder is advanced and we can loop. So let's see if this works. Okay, that compiled. So let's do like test lines, string reader. We can even make a function. String, and we do lines, and we construct the string reader from this string, and that's what we get. Okay, So now this wonderful automatic user interface, we can run test lines, and now we have a string. We can write new lines in this string. Hello world, bam, bum. It works. Okay, but there is a problem with this approach. Well, what are we going to be doing with the lines? We're going to be analyzing them further because we're going to be filtering them. And par has concurrent evaluation. So what will happen is that this lines function will like concurrently keep producing these lines, and then the filtering will run concurrently with that. But maybe this will run quicker, so we will get all these strings into memory that we are not catching up filtering. So the problem is that this list is like eager, that there is nothing pausing the creation of this list. So it will just keep being created regardless of if it is consumed or not, which could be a waste of memory. So what we want to do instead is we want to create like a kind of a lazy list that is only producing when we need it. Like the file may be large. We don't want to get 4 gigabytes of lines into memory without needing that. So we want to create the lazy list instead. So what are we going to have to do? We're going to make a custom type here. I'm going to call it iterator actually. Also, we haven't really handled errors here. So like this is also going to handle errors, and it's gonna have like some item type. Okay, so what is it going to be? Well, in par, nothing blocks, like everything runs concurrently. There is only one thing that blocks, and that is these cases. And that is both here and in the construction version for constructing choices. So when it comes to types, the only type that suspends execution is the choice type. That one like suspends execution until you pick a branch. So this is going to be some kind of a choice. And if you've been reading the documentation, you've definitely seen a lot of iterative choices, right? However, this is not going to be an iterative choice because an iterative choice is unbounded. But here we want something like a list, so something that finishes. So it's actually going to be a recursive choice. Neat, right? Recursive choice. What can we do with it? We'll be able to close it, which we get a unit, or we're going to be able to request the next element. Wait, does not just give us the next element. No, because it can reach the end. So it gives us an either. That's either an end, but if it's an end, it can give us a result of either an error or okay. Or it gives us an item A, and then we go back. So this type is like kind of much more involved than a list. So like in comparison, this is a list, but like it's not that complicated, right? Like it's, if we look here, and an item, they are here. And it just added these two methods here so that we can be requesting on demand. And also, instead of just like a boring end, there is a more funky end that can also have an error. This type is going to be like the heart of this demo. This is a very cool type. We're gonna squeeze everything out of it. So instead of a list here, we wanna return an iterator, and it will need to also have an error. So let's make this line generic. So this is a generic function now. So reader will have this error, and the iterator will also be able to do this error. Okay, so how do we need to modify this? We need to accept the type here as well. Reader begin, that's kind of fine, but we need to be producing a choice here. And we don't want to be matching immediately because we only want to be matching after we get told next. So we want to begin, okay, but we don't want to match here immediately. Instead, we want to like return a choice here, suspend, and then be able to come back to this begin anyways and suspend again. So here we're gonna take advantage of the process syntax and do a do, just like that. Do reader begin. Let's move this away for now. In. So this executes this reader begin as a command. That's the only thing that properly fits here. And then we're going to construct a choice, which is like the standalone case. Now, if we are closing, now we need to produce a unit, but that's no problem because reader can also be closed. So reader is linear, meaning if we just return a unit here, that will not work because we have not handled this reader. We cannot drop things like in Rust. There you can drop anything. So we're going to have to close it. Well, the close returns the unit, so we can just do reader close, and that's what we return as well. If we are requested to produce a next element, well, now we match. I'm gonna have to shift this. Yes, this IDE is quite not the best, but it's what we got for now. Okay, so now we match on the reader. That is after this begin. Okay, but now if the reader gives us an end, then we want to produce actually the same end with the same result. If we fail, we also want to get the remainder. Well, now the error is now very much possible. So in this case, we want to end and also with an error. And if we get the last line correctly, then we want to produce it. Oh, but what now? Can we do end here? No, because the self goes here and then we have a choice again. So we have to offer close or next again. Can we go back here to beginning? No, because we don't even have a reader anymore. We already consumed it here. So what are we gonna do? Well, we're gonna actually just inline here an empty iterator. We're just gonna do a case inline here, close. We don't do anything. And for next, there we do an end. This is an empty iterator inlined here. It's pretty neat. Okay, and so what do we do here? Here we produce a line. Oh, and then we reader loop. Back here, offer the choice again. Let's see if I have made any mistake. Oh, it compiles. Okay, wonderful. Let's check it. Test lines. We're gonna get a string. Gonna do lines. The error is nothing. String reader of str. That works. So test lines, we can again do hello world, blah, blah, bum, bum. Oh, but now it's very different, right? We put this input, and now instead of seeing all the lines immediately, we get these two buttons here, close and next. So if we do next, oh, it's hello. If we do next, it's world. Next, 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 and okay. So now we have a lazy iterator. Now, notice something pretty nice here. Like this iterator, it only exposes this next and close interface, but inside it moved this string reader into itself. So it's like pretty nicely encapsulated. And this string reader can be from a file. So actually this iterator will have an open file inside of it and reading it line by line on demand until it reaches the end or we close it. So that's pretty nice, I think. So this is like an interface, and here we made one implementation, another implementation. We'll have two implementations produced in the same function. Like, that's pretty cool. Okay, so we have lines here. What next? Now we will need to do some operations on that. We'll have to filter those lines and then also like add some line numbers to them. Well, let's go along with it. So let's write a filter function for this. Filter will be generic and it takes an iterator. Oh, and we'll put this box here, which means that we're only taking non-linear types, so those that can be copied and dropped. Then we need a predicate function. Box is like replicable anything, copyable, droppable. So this will be a function from A to bool, and it being a box means we can call it any number of times. And we will return an iterator. So let me just start writing it. Okay, so we have an iterator and we have a predicate, and we need to produce an iterator. So just like here, we are going to begin, oh, not the reader, but begin on this iterator, and then we're gonna construct our own choice. So if we are supposed to close, then we also close the iterator. Next, we need to call next on the iterator too. which is gonna give us either an end result, in which case we produce just that. But if we have an item value and iterator again, then now we have to check. Now we have to call the predicate value, and that gives us a bool. Now this is gonna get a little complicated here, but hang on, it's not that bad. So if the predicate gives us true, then we produce it and we continue back to here, back to offering the choice. But if it's false, you would think that this is the answer, right? That we just don't produce and instead we loop back. Well, it's not, because this would go into offering this choice again after not producing anything. Instead, what we have to do here is try pulling more and more items out of the original iterator until we get something, and only then we can go back to giving the choice for ourselves. So instead, what we have to do is actually start an inner loop here. This is a label here, where we just ask the next item from this iterator, and if it's AND, then once again we AND. There will be some code repetition here a little bit. I'm not sure I can do it without the code repetition, or it gives us a value. If it gives us a value, we once again need to call the predicate. This is the code repetition, like calling here and here. I would love to see it done without that repetition, but I was not able to fit that into doing these begins properly. Okay, so if it's true, then we're very good, and we go to this proper loop again. If it's false, then now we go to looping back to skip. So looping back to here. So this little inline loop here will just pull elements out of this original iterator until it hits one where the predicate holds. And then we go back to this. Otherwise it will keep looping here. So does this compile? Yes, it does compile. Okay, so let's maybe start now writing the actual program. We will need a couple more helper functions later, but we need to, well, open some files and read them. So let's start by traversing directories. So there is this storage get function, and it takes a string path, and then it will, well, it can give us an error, okay, if there is nothing there, or it can give us a file or a directory. And this is appropriately called file info and dir info, because that is not an open file. That is just like an information about a file or information about a directory. Well, see that this is a box choice, meaning, well, this box, remember, is like something that you can use many times, because normally a choice is linear, so it can only be used once, or like you get back to like somewhere via recursive iterative. But a box can be used many times on its own, and so you can get a path out of it, or a size, or you can turn it into a reader. And the storage is recursive box choice. That's something, right? You can also get a path, or you can list it, which can also give you an error, but also it can give you a list of files and directories. But also, since it's recursive, that is also telling us that this self, like this loop here, can only be done finitely many times. And that's because if we are not following symbolic links, then actually directories should be like a well-founded tree, right? So you should not be able to go into a subdirectory infinitely many times. And so that's reflected here by it being recursive. So let's actually start writing a program. So we're gonna write a program. It's gonna be a unit. We'll see that this is now something that we'll be able to run from the command line. We're gonna do a chan here with exit. A chan, as you know, is like an inverter expression where like we construct something via a process here that has like a callback to the consumer. And since we are producing a unit here, this exit is actually of the continuation type. Which, if you read the documentation, know that the only command in the processes for a continuation is the break command, which is spelled like this, and that actually exits the process. So this is actually exactly what we need. So, and we'll be able to exit it prematurely as well. Okay, so we want to be writing to the console. So for that, here we find the console interface here, but also console open, which gives us a console. So we need to instantiate a console, and then we can use it. So that's an iterative choice, iterative co-recursive. So that means that we can be looping it as many times as we want. And so we can print stuff there, or we can prompt, which gives us some result. And this self always loops back to this iterative. At the end, we need to close the console because it's a linear type. So we need to close it. Okay, so now we're going to print welcome to mini grep. Bam. It's gonna be a program like this. And now say we want to get a path from the user that we are going to be traversing. So console prompt, some prompt string here. So path. And that gives us a pair here of potentially read line with a unit error. So there it can be like fail to read, and the remainder of the console. So we could do like input console equals this, and that would work just fine. But in process syntax, we can also use the receive command to achieve this same thing. So instead, we can do square brackets and input. That is the same as this, but it's like nicer here, and it's actually a more fundamental syntax. Like this is actually a syntax sugar for this. And so now we can case on it here. If it's an error, well, then we can print failed to read input and close the console and exit. And if it's okay, then we have a path. And then we do empty curly braces here, which fall backs here. And the way scoping works in PAR is that it's like process scope. So since this continues here, this variable is available here. So we can print it. Let's try to run this just so we see that it works. Parlang, now run, mini grep. And we want to run this program. So that's what we write here as well. Welcome to mini grep. Path, whatever, because we're not doing anything with it now. Print whatever back exits. Okay, so but now that we have a path, we can do something with it. So let's first traverse it and print files that are in the directory nested as well. So how do we do that? We need to storage get. Let's do like traverse, which gets a path and gives us a list of file info. And so now we storage get on that, and it can give us an error. Let's ignore it now. Let's just give an empty list if there is an error. And if there is okay, then there is some item. And so we case on that item because that can be a file and a directory. If it's a file, then we have a file info. So we make a singleton list like this here. And if it's a directory info, okay, now we have to traverse a directory. So let's actually make a function for that. Traverse directory, which gonna take storage directory info and return a list of file info. Okay, so directory. So what is the directory info? It's a choice so that we can list. Okay, so we can list it, and then also can be an error. Let's again ignore this error for now at least, and or it can be okay, and then there is items, and those items can be files or directories. So we can start looping here on this list inline because we have inline recursion. If it's empty, then we are empty. If there is item, then we go here, and the item once again can be a file, in which case we produce the file and we loop back on this here, or it can be a directory. And well, in that case, we have to be careful because now we have both this directory and the rest of the items in the original directory. So we have to do both. So how are we going to do that? Well, this is a directory, so we want to recursively, we're gonna do a begin here because it is recursive, and we need to label it because we now have nested loops. So recursively, this is going to get us the list of files of this nested directory, but then we also have the remainder of items from the original directory, rest loop. So we have to actually concatenate these two lists. So let's make a concatenation function for lists. Gets to lists, gives us another list, left, right. Now this is a simple exercise, so we just loop on the left list. If it's empty, then we give the right list. If it's not empty, then we produce the item and loop on XS. So here we concat generic, so file info, and that should work. It compiles, okay, it type checks. So that's great. So instead of printing this path, we can traverse the directory and then print all those files just to test that it works. So if there is nothing, then we do nothing and we fall down here. If there is something, well, file info and rest, then we are going to print the, well, what is this path here? It's a path info which can give us a name or an absolute path. So we'll get the absolute path. So we're going to print that and then rest loop. Something went wrong here. Oh, because let's do traverse instead of traverse directory. And that's all right. Let's see if it works. Oh, there we go. So wonderful. Now that we have all the files, we can start grepping on them. So let's now make this grep file, so which will take a file info, and we're just going to return a list of strings here, or actually not the list of strings, but also with line numbers. So this is a pair and it's going to give us like a line number and the content of the line. Oh, and also here we need to do the argument, the query string that we're searching for. In this file, search for this string and give us all the lines that match with their line numbers. So grep file, let's call this a needle, and file info. So how are we going to do this now? Well, we already have this lines function. So let's switch here to process mode. We're gonna fill this in later. Okay, so first we're going to convert this into lines. Okay, so lines takes an error type argument. So that's storage error, which as you can see here is defined as string. And we need to give it a reader, which file info can give us a reader. So file info read UTF-8. Oh, but that's a result. So that can fail. So we have to, okay, actually we have to do that a little differently. So in case we failed to read, just return an empty list. And if we did not fail, then we have a reader. And now we switch to process syntax. So we make lines. Okay, so what do we need to do now? Well, we cannot filter yet because we would lose the information about the line numbers. So instead, we first have to attach line number information to these and then we filter them. So let's make another help function here. Enumerate one, like because we're gonna start from one, that's going to get an iterator and give us back an iterator with numbers. So we get an iterator here, and a similar pattern as here, like we have to loop on this input iterator, but at the same time we have to be offering choice to the consumer, like we have to be producing an iterator ourselves. So we begin here and then we case. If we close, then we close. If we request the next item, then we request it from the iterator as well. If it gives us an end, then we produce that end. And if it gives us an item, then we produce that item. Oh, but now we have to produce a line number here. So how do we do that? So we're gonna have to be incrementing something. We just make a variable, let index starting at 1 here. Then we produce that index and a value. And now we have to loop back, but we have to increment the index as well. So I'm just gonna do it nicely like this here, that let index equals, we're going to add 1 to it, and then we're going to loop back. So just like that. And this now properly attaches line numbers to this iterator. So right after here, we're going to reassign here and enumerate 1. Yes, these generics are a little unwieldy because they are very explicit, so you always have to supply the type arguments, which can get a little uncomfortable. Hopefully we're gonna resolve that in the future for par by adding some type inference, but for now it's all very explicit. Okay, so lines, that gave us an iterator of over a string. So this is the second type argument here, and we're passing in these lines. Now we have to actually filter the lines for those that contain the query string. Well, we already have a filter function, but we need to supply it a predicate. Well, the predicate, of course, is that we need to search for this needle. So let's make another little helper function, which is going to be like contains, which takes 2 strings and returns a bool if this one is contained inside this one. This would normally be like a standard library function, but par is very small right now, so we have to do it manually. So needle, haystack. We're going to use this reader again for that, but we're going to use a different pattern. So we're going to make a string reader for this haystack string. So there we go. And we're just going to do 1 match on it. Let's make this a little nicer here. The string can start with anything, but then it needs to contain the needle. So anything is repeat 1 any, and then a specific string needle. This is what we will match on. So if there is an end, then the answer is false. If we fail to read, then the answer is false as well, but we need to close the reader because it's linear. So reader close, and the result is false. And if there is a match, we don't care what the match is. We just also need to close the reader, and we return true. So that's the, oh, we have a error here. But if I comment this out, then I have a program, because not failed, but fail. There we go. Okay, so we can test this function. Not sure why this got so small now, but we can test it. So hello is contained in blah hello world. True. Hello is it contained in blah world. False. So that works. Wonderful. Okay, so now we have a function to check strings. So now we can get back to this and we can filter them now. Okay, this is gonna be a little eyesore for these type arguments. But so what does this give us a filter, needs an error and an item. So storage error, and these are now these pairs. We are filtering lines. Now the second argument is of course the function. So, and it's a box function so that it can be called any number of times. So which we construct with box, which receives the pair, the number which we're going to ignore, and the line content, and we return contains line, or needle is the first argument, line. That filters that. Wonderful. Now that we have filtered lines, but here we want to return a list, so we need to turn this iterator into a list. So that's pretty easy. We start the loop on that iterator, and we just call next on it, and then there can be an end. Once again, let's ignore the error. So in this case, it's an empty, or there can be an item line. That's a pair, number and the line, but let's just put it into a single variable, rest and item line, rest loop. So that's just how we do it. It does not compile because this is file info. There we go. So now, instead of just printing the file path here, we can actually go print these. Let's set up a nested loop here. So grep file. Oh, and we need to ask for a needle as well. So let's just copy paste this, like why not? Needle, failed to read input, needle. Now we have a path and a needle. So we grab this file. Now we have a list back, so we loop on it here, but that's gonna be like file so that we can distinguish these two loops. If we reach the end, we just proceed. Otherwise, we have a line number and a line content and remaining lines. And so here we want to print that to the console. Just so we have some spacing, let's first print an empty line. Then we want to print the path of the file and the line number. So we don't have formatted strings at the moment, but we have a string builder which can help us build a composite string. We use a string builder here, add file info path absolute here, then we add colon here, and then we add this line number. So we convert it to string, and then we build the entire string here and print it. And finally, we print the line content. Print line content, and there we go. That compiles. I'm lucky today. Like everything compiles that I do. So is this all? We ignored a lot of errors here. So let's just debug log an error here, just so we know. There could be an error here, so let's also debug log that here. Debug log error. Oh, do. Okay, there we go. Also in here. Okay, I guess that's probably gonna be sufficient. Okay, so let's try it. Let's try it. Clear? There we go. Okay, what are we going to be searching for? Result expression. Bam. We just found one. That does not seem right, right? Or is that actually correct? No, that's definitely not correct. And what file did we find it in? In parse rs, which is this file. So we have some problem. Of course, the problem is that I didn't loop here. So remaining lines loop. I only printed one line and then went off. So loop file, it's this loop. Okay, there we go. So now it should be a little better. Yeah. Oh, there we go. Okay, so this actually printed a lot of things. So this works. Wonderful.